Hey there, Mr. Weaver here, and this is lesson 3 of topic 4b with compound inequalities. After this lesson, you need to be able to solve compound inequalities, and you need to be able to graph the solution sets of compound inequalities. You'll know you're successful if, after this lesson, you can solve and graph the solutions for compound inequalities and understand the difference between and or statements in compound inequalities. A compound inequality is a number sentence with two inequality statements at the same time. The word and indicates that both statements must be true at the same time. And if you see the word or, that indicates that only one of those statements has to be true. When we're graphing, there's generally going to be two different looking graphs that you're going to come across. Now, these aren't the only options. However, these are the most common for compound inequalities. So the first type of graph is where it looks like there's two outer boundaries and not really an arrow. Well, the arrow is actually in between and they're pointing at each other and they kind of stop when it gets to the other boundary. So you don't really see the arrows. But this graph is an and graph. An example of this would be to be considered a teenager. You're at least 13, but you're at most 19. Okay, you have to fit both of those things to be considered a teenager. The other graph is our or graph. And here we can see the arrows and they're kind of pointing outward away from each other. Now, or graphs can be a little more complicated because as long as one of them is true, it doesn't matter. So the arrows can kind of go any way they want. They could both be pointing the same direction or they could both be pointing opposite directions as long as one of the things is true. But if you see this type of graph, it's a clear indication of an or graph. There's no possible way for you to be smaller than a number. So let's say if that closed circle there was at 2, and larger than a number that was larger to begin with. So there's no way possible to be smaller than 2 and larger than 7. Okay, so if you see arrows pointing away from each other, that's a pretty good indication that it's an or. An example of this would be at the movie theater. For discount movie tickets, you must be under 12 and you get a child discount, or over 65 for that senior discount. So as long as you fit one of those two things, then you're going to get the discount. When we're solving compound inequalities, all you're really doing is just solving two inequalities, and then our graph, we graph them on the same number line. So, first example here, solve 5x minus 7 is greater than 13, or negative 4x plus 3 is greater than negative 5. This doesn't mean that you get to pick which one you want to choose. It means our answer has to be true for one of those or the other. So if we solve them both, we can figure out where our numbers can fall in. So first, solving the left, I would add 7 to both sides, get 5x is greater than 20, divide by 5, so x must be greater than 4. So that's one of my possible things that could happen. X could be greater than 4. If it is, it works. To figure out other possible things that could fit our solution, I solve the other thing. So subtract 3 from both sides. Negative 4x is greater than negative 8. Divide by negative 4, and I get x is less than 2. Don't forget to flip the sign. We divided by a negative. Now, because this says or, as long as one of those two things is true, then our inequality is true. So what this would look like on a graph, we would just graph them both on the same number line. So the first one says x is greater than 4. So I would put my first inequality, open circle at 4, and x must be greater, so it would go to the right. My other inequality is x is less than 2. So I would put the other one, open circle at 2, with my arrow going to the left, so that way x could be less. When I'm testing a solution, as long as it's somewhere in one of the arrows, it's fine. So here, it could be less than 2 or greater than 4, and it would work. Anything between those two numbers is not true for this solution. Pause the video and try it out for yourself. Solve both inequalities and graph it on a number line. Again, just because it says or doesn't mean you pick which one. You still need to do both. Let's check through. So solving on the left, you should have got x to be greater than or equal to 4. We had to divide by a -10, so we had to flip the sign. For the other one, you should have got x was less than or equal to -5. We didn't divide by a negative, so the sign stays as it is. Graphed, you should have had both closed circles. So one of them at 4 with your arrow going to the right, and the other at -5 with the arrow going to the left. Let's look at an AND example. So solve 3x plus 4 is less than 16 and -3x plus 2 is less than or equal to 17. So again, we need to solve both things. The AND is not telling you that you have to solve both things. It's telling you that the solution has to work for both things. So we'll start with the left one. Subtract 4. 3x is less than 12, divided by 3. X must be less than 4. Sign stays the same since we didn't divide or multiply by a negative. Right side, subtract 2, divide by -3, and flip the sign since we divided by a negative. When we're graphing this one, here's how the AND actually looks. So if we graph the first one, I have x is less than 4. So if I were to graph it, open circle at 4, arrow to the left. The other one would be x is greater than -5. So it's a closed circle at -5, and since x is greater, the arrow goes to the right. What ends up happening is, in order for it to be less than 4 and greater than -5, once it gets to the other boundary, it can't be true anymore, and so the arrows kind of stop at the other circle. So we combine them together, so the line is the arrow, and it's just between those two circles. So again, it was 2 arrows, and then once you get past the other circle, it can't be true anymore, so it just stops at the circle. Pause the video and try the second one here. See if you can figure out what the graph of your solution should look like. Check your answers. First one, you should have got x was less than or equal to 2. Second one, you should have got x was greater than -5. Neither sign switches. We didn't divide by any negatives. When you graphed your solution, it should have looked like this, where you have an open circle at -5, a closed circle at +2, and your arrows are cut off between those two numbers. Just like with the last example, don't assume that an AND statement is going to be between two numbers. They could theoretically both be pointing in the same direction. So please double check and graph on a number line to see what exactly your solution graph should look like. Finally, let's look at how some solutions fit into this. So which values of x below fall within the solution set of -16 is less than 7x minus 9 is less than 12? Select all. So there's 2 parts to this problem. Let's ignore our answer choices for now. If you come across a statement like this is actually an AND statement. Because of where your x is located, So in the end, when you are coming up with your final boundaries, x is in between two numbers. So here it's disguised as saying x is between, so it has to be greater than or equal to negative 16 and less than 12. And we need to figure out which value of x stays between those two numbers and fits both things. So here's how this is disguised. It's two inequalities smushed together, where the middle goes with the left and the middle goes with the right. So that 7x minus 9 is in both inequalities. Then when we go through and solve, I just solve both of them like we've done before. So on the left, I would add 9 to both sides, get 7x and negative 7, divide by 7, because that's the number in front of x. X is greater than or equal to negative 1. The good thing with these inequalities is when we're solving them, it's the same steps both times. So I would still add 9 to both sides, still divide by 7, and get x is less than 3. Remember, this is an and situation. So x has to be greater than or equal to negative 1, and x has to be less than 3. Our final solution that we should write, we would put the two things back together, and this time, since they have the x in common and they overlap, okay, I can kind of smush them back together. So I started with two things, smush them back together, and I'm back to one inequality that fits both things. So I would read this as x is greater than or equal to negative 1 and x is less than 3. If we were to graph this on a number line, we would have a left boundary circle at negative 1 where it's colored in, and we would have a right boundary at 3 with the arrows between. So it's showing that our solution must be between negative 1 and positive 3, and it's okay if our choice is negative 1. Which of those fit into this inequality? So we can go through and just check each one. So first one, x equals negative 3. Is negative 3 between negative 1 and positive 3? No. What about negative 1? So negative 1 is where that closed circle is. And remember, a closed circle is part of the solution. So negative 1 can be part of the solution. What about 0? 0 is definitely between those two numbers. So yes, we'll check that one off. What about 1? Again, 1 is definitely between. So now 3. 3 has an open circle at it, which means it cannot be part of the solution. So I would not check off 3. And then 5 would be too much because it's not less than 3. So I would only choose those 3 numbers that fall in the solution set. Those are my only 3 numbers that are greater than or equal to negative 1 and less than 3. Your turn one last time. Pause the video and see if you can figure out which of those numbers fall within the solution set to that inequality. Let's check. So again, this is an and, so you should have split it. The middle goes to both things, but everything else stays the same. When you solved the left inequality, you should have found x was greater than negative 4. The right inequality was x is less than or equal to 2.5, which means your combined inequality would be negative 4 is less than x, which is less than or equal to 2.5. So which of those things fit in that solution? You should have chose the top 4. In this lesson, we learned that compound inequalities are just two inequalities together at the same time. If the compound inequality uses the word or, then the solution just has to work in one or the other. On the other hand, If the compound inequality uses the word and, then what you get as your solution or what you're testing as your solution must be true for both inequalities. Compound inequalities are also graphed on the same number line. So OR situations are generally going to be pointed outward, but not always, while AND are generally shown as a line between two boundary circles. You don't see the arrows because they get cut off at the other circle. However, since these aren't always the case, you should definitely graph based on what you get as your boundaries. Don't just assume that it's going to always look the same way. And finally, we learned that combined compound inequalities, such as 0 is less than x plus 3 is less than or equal to 8, those are just disguised AND statements. So if you see that and there's no word AND or, it's an AND statement. And then the middle part here, x plus 3, would be included with both inequalities. If we need to solve those, you just split it apart and solve it as two different inequalities. So after this lesson, do you now know how to solve and graph compound inequalities? And can you tell the difference and know the difference between and or statements, and then determine if a value is part of the solution set? If you're not sure about these things, go back and watch some of the examples on the differences between and or graphs and how you can tell if something is part of the solution. And that's the end of lesson 3 on compound inequalities.